Cytochrome C peroxidase is a water-soluble heme-containing enzyme found in the cytosol. This belongs to the peroxidase family. It takes up electrons from cytochrome C and reduces hydrogen peroxide to water. Cytochrome C is a heme protein and is present in the inner mitochondrial membrane and is an essential component in the electron transport chain, which carries out single electron transfer reactions. The enzyme's primary function is to eliminate toxic radical molecules produced by the cell, which are harmful for the biological system. CCP and Cyt-C are 361 and 109 residues long proteins and are about 40 kilodaltons and 12 kilodaltons.
The main component in cytochrome C peroxidase is a heme group which serves as the active site. Heme group consists of a porphyrin ring surrounding an iron atom in +3 oxidation state. The interplay between the oxidation states of the ion center is crucial for the activity of CCP peroxidase. The mechanism of catalysis proceeds through 4 important compounds. In the resting stage, the active site has an ion in +3 oxidation state. The hydrogen peroxide then attacks the ion center to form an octahedral compound 0. It then loses a water molecule along with oxidation of the ion center to +4 to give compound 1, which is a radical cation. A single electron process takes place to give compound 2, which is an uncharged ion in +4 oxidation state. Another single electron transfer then takes place along with water loss to regenerate the active site in its resting stage. Each step of this cycle will be explained in detail now. The ion center has its axial ligands as histidine 175 of the protein chain. The other amino acid side chains in the active center include histidine 52, arginine 48 and tryptophan 191. In the resting stage, CCP has a distal histidine 52 that is not bound to the heme ion but is intimately involved in catalysis. The hydrogen peroxide, after deprotonation by the histidine 52, becomes more nucleophilic and attacks the ion center to form compound 0. The conversion of compound 0 to compound 1 requires protonation of the distal oxygen of the ferric hydroperoxide complex so that formation of the ferryl species can be linked to elimination of the distal oxygen as a molecule of water. It is thought that the distal histidine residue in the peroxidase active site is the base that deprotonates the peroxide in the formation of compound 0. This proton is then delivered by the imidazole to the terminal oxygen of the ferric hydroperoxide complex, catalyzing the OO bond cleavage that produces compound 1. Compound 1 exists as a radical cation with the ion center in +4 oxidation state. The radical cation in CCP does not form a porphyrin radical but instead forms a tryptophan 191 radical.
Let us see what facilitates the formation of compound 2. This step requires addition of an electron to compound 1, which happens after formation of CCP Cyt-C redox complex. The basis of this complex is non-covalent interactions. Studies showed that complementary electrostatic interactions play a major role in the formation of this redox complex. By the virtue of these interactions, several modifications such as ordering of solvent molecules and increasing proximity of aspargine 194 and heme group of Cyt-C protein are seen. Electron transfer occurs from Cyt-C to CCP without formation of any covalent bonds. The following animation is not the true representation of electron transfer. Fe2+ in Cyt-C is oxidized to Fe3+. The porphyrin ring transfers this electron to aspargine 194 by virtue of its proximity. The amino acid chain from aspargine 194 to tryptophan 191 is already ordered in compound 1 due to formation of tryptophan 191 radical. This leads to transfer of electrons from aspargine 194 to tryptophan 191 radical, which further transfers it to peroxidase ferryl group. Another similar single electron transfer sees the return of peroxidase to its resting state and the loss of oxygen as a water molecule. Despite decades-long worth of efforts, the exact electron transfer mechanism in non-covalent CCP Cyt-C complexes still remains a challenging and intriguing problem.